a genuine pleasure to introduce this guy, Yair Siegel, and I have worked together. They were one of the very earliest members of what was then called the Embedded Vision Alliance, now the GIM Vision Alliance, and we've worked together for a number of years. Yair is Senior Director of Business Development for Ceva. The title of his talk is NeuPro-M, a highly scalable, heterogeneous, and secure processor for high-performance AI, ML, and smart edge devices. And what I will say by means of introduction is that we announced the yearly 2022 edition winners of the Edge AI and Vision Product of the Year Awards last night. And this product from him was the runner-up in the Edge AI processor category. And without going into details, it was a really tough competition. So that he was runner-up was nothing detrimental at all. A very strong architecture and a very tough decision for the judges. So he'll tell you a lot more about it next. Thanks.
Great, thank you, Brian. Good afternoon, everyone. It's great to be here again. It's been a few years, of course. And as Brian mentioned, Ceva and myself have been in long partnership with the Embedded Vision Summit, and we're happy to share more details on our latest AI processor called the NeuPro-M. So today I'll go over that and share with you a bit more details. And I wanted to start about sharing a bit of what we see in the market in terms of the AI challenges. So the market has grown a lot in the last couple of years, which is great. But we still see that a majority of the use cases for what we're looking at is still coming from computer vision. And if we take as an example automotive as a market, this is one of the markets that we target to serve. So the automotive market, we see more sensors coming out in the automotive. Each of the sensors, more sensors means that we need to use more pixels, and this generates more data. And eventually, it leads to a need for much higher performance in the market. A second item that we see is if we continue with the example of the automotive market, so even there, within the automotive market, we see a bunch of different use cases that need to be handled and a bunch of different levels of compute that we need to address. So for example, if we look at the compute for ADAS and compare it to compute for level 4, level 5, or to powertrain, infotainment, or driver monitoring, they need very different use cases and different levels of compute. That means that a solution for this market needs to be very flexible and scalable as well. Of course, many of the devices or most of the devices that we work on are battery powered, so they are constrained in terms of the energy. So low power is always key for such technologies. Then when we talk about AI, even after close to 8 years, at least that we've been in the market pace has not slowed down, so the technology evolution is very fast, and actually it is much faster than the product deployment. That means that we need a solution that will remain concurrent active for quite a long time, so we need a flexible solution. And finally, software is key. So software needs to be very comprehensive, needs to be aware of the hardware that is in the embedded solution, and it needs to address the trends that are going on in the market and continue to be updated and utilize, basically enable the developers to take what they have and to quickly move to the hardware abstraction layer and be able to address the new features that are coming out all the time. So when we talk about Ceva's approach in the market, we took all of these challenges and we addressed one by one in the NeuPro-M and made sure to optimize for power, to optimize for low power and optimize the performance of the solution. So let's go over each of these on a high level, and then I'll elaborate in the next couple of slides. So the NeuPro-M is actually a heterogeneous processing. I know many people know Ceva as the DSP company, but over time we actually supply a lot of compute elements that are not DSP, and this is also the approach we took with NeuPro-M. It's a combination of multiple compute engines. We have multiple tiers of compute. So we actually, one of the compute solutions is we call it an engine. So it includes inside the engine multiple compute blocks. And we have an ability to scale up the number of engines, so we can use multiple engines within a processor. And then we can use multiple processors within the SoC. So 3 levels of scaling up. So this will enable very good performance compared to our previous generation. The second area that we invested a lot is build a multi-tier solution for multi-memory solution structure that enables to hide the latency between the different elements and between the different memories, and also lower the memory bandwidth. In addition, we support compression of data and weights, and we also support different types of sparsity. We will see that, which is done on the fly without a need to go back to the memories. So this again optimizes the bandwidth, which eventually will also lead to lower power consumption. We did add to the NeuPro-M solution capabilities to address things like secure element and also addressing automotive ISO 26262. These and other mechanisms enable us to address, again, a bunch of different use cases, automotive, security, surveillance, and other market as well. So very flexible in that element. Eventually, when we talk about neural network, there are many different mechanisms, and we added a bunch of different compute elements, as I mentioned, that tackle some of the new technologies that have been coming out recently for neural network. And this is part of the solution that we have. We also have a vector processor unit in each of the engines that I mentioned, and this will give you flexibility to run any new layer that will come out even after you have the hardware available. So this will enable a long-term solution. And finally, when we talk about software, so we have our CDNN tool chain. It stands for Ceva Deep Neural Network. So the front end of the CDNN will plug into open source frameworks, real-time operating systems, and environments. And the back end of the CDNN is basically optimizing for the hardware, and it has the real-time implementation in it. Both together will enable easy migration for developers from their existing trained network to an optimized solution that is running on the hardware and efficient, and continue to work as the development of the program continues. So this is the approach that we took with the NeuPro-M. Let's look a bit at the details, technical details of the NeuPro-M. So if we look at the solution, I mentioned that we have the engine of the NeuPro-M. So the engine within a core, basically a single core, can run between 8 to 160 TOPS. And then we have scalability of multiple cores within the SoC. We can go up to 1,200 TOPS. And we can run different neural networks and different algorithms, of course, and very flexible. If we look at a typical network, so a typical network running on the NeuPro-M, we will be able to get to very high utilization, typically above 90% utilization of the hardware. As an example, running a ResNet 50 on the NeuPro-M, we're able to achieve 24 TOPS per watt on the solution. And basically, that beats our previous generation, the NeuPro-S, by 5 to 15x in performance, and reducing the memory bandwidth by over 6x. So that shows the efficiency of the solution compared to our previous generation. Let's dive in a bit to the architecture itself of the NeuPro-M. So the architecture actually has 3 main blocks: the NeuPro-M master controller, the NeuPro-M engine, which I mentioned a bit, and the NeuPro-M common subsystem. So it's quite a unique and multi-tiered solution. So let's start with the NeuPro-M master controller. So this is basically running what I mentioned, the CDNN runtime, and distribute the compute to the other elements. The NeuPro-M engine is the main compute portion of the NeuPro-M, and it includes different blocks of compute. So we added here, we can see 6 different compute blocks. One of them, the vector processor unit, is more of a programmable solution, and the rest are really hardwired tiered to specific implementation and specific function. So the engine, a local controller, is basically distributing the data to the different solutions and running them. We have the mixed precision neural engine, which includes the 4K MAC capability, the grid. And then we have the activation complexity unit, which basically can do support for sparsity, both structured and unstructured sparsity. And we're able to run that on the fly without need to go to the memory. We have a dedicated unit for activation as well. And we have a dedicated unit for Winograd, which I'll mention in the next couple of slides. And then the VPU, as I mentioned, is the unit that will run new layers that are coming out, after the hardware or the silicon is available. All of those are basically working on the same local memory, which is shared. I'll call it the L1 memory. And all of this engine, we can basically connect to or scale up to have between 1 to 8 engines, depending on the configuration of the SoC that is selected. And then the last portion of the NeuPro-M is the common subsystem. The common subsystem is basically controlling the different engines. So it has a block that is called the multi-engine controller, which takes care of the control. We have a shared memory here, which we call it L2 memory. So the L2 memory, the goal is to minimize the access of the engines to the external memory. So the NeuPro-M common subsystem is the one that accesses the external memory or the DDR, while the engines themselves do not need to access that. So reduce the access to the actual DDR, reduce power. And then we also have different interfaces that go to different peripherals within the SoC, all of that within the common subsystem. Okay, so let's look a bit about the different feature sets or key features of the NeuPro-M and how they scale for the different targets that we talked about before, like performance, like power, like low bandwidth. I'm not going to go over all of these features, but I will talk about the sparsity. I'll talk about the different mass support. I'll talk about, of course, the tools, and I'll talk about the control scheme. So we'll go over those in more detail a bit. So Winograd, Professor Winograd is invented a very interesting algorithm that essentially takes the convolution capability and does the same job with half of the compute needed. So in the NeuPro-M, we utilize this capability, but we did a very interesting implementation, mostly focused on 3x3 convolution. But we're able to support different data types from 4-bit up to 16-bit. We do not need any additional guard bits for implementation. We were able to achieve a very good performance, so we do not have any degradation, any significant degradation in terms of the precision using the Winograd transform. And we do not need to do any retraining in terms of using it. So as an example, using running ResNet 50, we're able to achieve 30% improvement and 80% improvement for YOLO v3 just by enabling, turning on the Winograd transform. So this capability can basically be turned on and off per layer level. Same goes for sparsity. So sparsity is the idea that the compute will actually skip data or weights that have 0 inside them. So quite a few solutions in the market support structured sparsity. However, structured sparsity, as you can see in the graph, only applies to 2 weights. We support that, but we also support unstructured sparsity, which utilizing this capability, we can address good performance gain of 2 to 4x, both for the data and for the weights. So that's a powerful feature within the architecture. And as I mentioned, we have a dedicated block which is doing support for this sparsity. For data types, the NeuPro-M neural engine is basically a 4K MAC grid, but this is 4K is for 8-bit. So we have different types of support. As you can see here, we support from 2x2 up to 16x16 fixed point, and as well as half precision and single precision floating point. that what is interesting for the NeuPro-M is that we're able to switch the precision per layer basis. So for example, if we're able to switch for the network 4x4 compute versus 8x8, we can gain 4x in terms of the compute. Of course, that will lower the bandwidth, it will reduce the power consumption and improve performance significantly. Let's look at a little bit about performance. So if we take some example networks such as ResNet 50 and YOLO V3, so here we're looking at NPM11. So NPM11 is the lowest end of the NeuPro-M. It includes single core and single engine. It can achieve 20 tops, up to 20 tops. And if we compare this performance on this core versus our predecessor, the NeuPro-S, which is here in gray, we can achieve between a 5 to 15x performance gain. So 5x is roughly using the base mechanisms, and we get up to 15x when we enable Winograd, Sparsity, and 4x4 MAC on some of the layers. So this is a great jump in performance versus previous generation. I mentioned before that we have a dedicated control scheme that is basically enabling to utilize all the different hardware blocks that we talked about. This is a combination of software and hardware. And essentially, one of the features that it enables is that we do not need to redispatch the program on the different layers. In addition, the compute, this control scheme enables the NeuPro-M to do on-the-fly processing, what is called head-to-tail. And we basically pipeline the operation of the different layers without the need to re-access all the memories. So this significantly will reduce both the internal as well as the external memory accesses. So this is very important feature, and it really enables, it's an enabler for the software tool set to utilize all of the hardware pieces within the NeuPro-M. So now that's a good segue to talk about the software. So our NeuPro-M, a comprehensive toolchain, leverages on years of experience of our CDNN tool. We continue to improve and utilize the capabilities. And some of the things that we have today are listed here. So first we have the neural network training optimizer. So this is the idea of having the tool that is, as part of the training, it's hardware aware and it optimizes for the hardware. Then the second stage will be to utilize our system architecture planner tool. So it gets as an input the image as well as the parameters of the system and the architecture that you are using. And it outputs different statistics, including the cycle count, including the accuracy, including the traffic, and then the user can optimize his architecture, can optimize the network according to the system planner output. The third stage will be to offline optimize the network using the CDNN toolset. It basically merges layers, optimizes for the hardware, etc. And finally, we are taking the CDNN runtime and actually running it in the hardware. So all of those are very comprehensive, and we can work as a standalone solution in terms of the tool, or, and as mentioned in the next slide, we can connect the CDNN to actual ecosystem, open source ecosystem, which is also very important and critical in the market today. There are many different operating system tools, frameworks, and neural network APIs that are available. And at Ceva, we work very hard on that in terms of supporting new things that are coming out. The CDNN front end will connect to such networks such as TVM, Glow, and Onyx, and then the back end will basically enable to run it optimized in terms of the memory and the load balancing on the processor itself. So if we look at the solution today, to summarize the NeuPro-M, if you look at in general for AI architectures, if you have a single bottleneck, it will greatly affect the performance. So what we did for the NeuPro-M, we actually went and optimized our solution for every different area and every different layer, and try to open up all the bottlenecks that we saw in previous generations, as well as different networks and different technologies that are popping up in the market. So starting with the data and weights, I mentioned the ability to have a mixed precision. And very flexible fixed point as well as floating point solution, supporting unstructured sparsity as well as structured sparsity. Looking at operations, so we do have direct support of the hardware blocks for different key technologies for neural networks, such as Winograd, such as depth-wise, such as transformers and 3D convolution. From data bandwidth, we talked about a capability of the solution to basically have a streamline the compute engine. So we have a multi-tiered memory structure to do that. We also do optimization of compressing and decompressing the weights and the data. And all of that will enable to lower the data, especially to the DDR, which is of course very heavy in terms of power consumption. We basically invest a lot for the control flow of the processor. We have dedicated units for that, both on the general system as well as the specific engine that we have multiple of them. All of that will again enable very efficient solution and will also help to enable the tool set to utilize the different hardware blocks that are in the processor. So that's a key. And talking about the hardware processor, the software tool set, we actually able to utilize the hardware awareness from the toolset level. So we continue to evolve from the CDNN compiler into additional features, into supporting open source networks. We have dedicated unique features. For example, the CDNN invite is one of the unique features of Ceva that we're able to get as input external AI accelerator. So let's assume that someone has their own AI accelerator and they want to plug it in addition. Maybe this accelerator tackles very efficiently a use case that maybe we did not think about. So we can do that and plug it into the tool set and still use the CDNN with that. So that's one of the unique features, and we have additional, many other features like asymmetric quantization, pruning, etc. All of those together make the NeuPro-M to be very unique solution in the market, but yet very flexible and efficient to address the different use cases, the different markets that we work on, and our customers, of course, are interested in. So that's about it for the NeuPro-M. If you have any questions, happy to answer, or if you want to talk, I'm just around the corner in our booth. Thank you.
Good job. Applause. We've got about 5 minutes for questions. Draw your attention to the microphone in the center of the room. Please queue up, and I'll start. So, as I mentioned in the intro, you and I have worked together for a long time. Ceva has been in the DSP business for a long time. Ceva was one of the first AI inference IP suppliers in the space. Obviously, you got a bit more competition now than you did back in the early days. My understanding, and please correct me if I'm not spot on, is that through multiple generations, you've evolved off a base architecture foundation, right? Some of these other approaches that are out there are more what I call revolutionary, right? They kind of take more of a clean slate approach. Can you talk about the approach of a long-standing player in this space like you versus a more, revolutionary, newer alternative that comes in, both from a software and a hardware standpoint? And the other part of it that I'm curious about is, how have you been able to evolve your architecture as workloads change, as requirements change, as the whole scope of deep learning has evolved?
Yeah, first of all, good question. So you're correct. So we were the first that are doing actually Edge AI. Back in 2015, I think I presented it here at EVS, probably end of maybe 2015 or 2016. And we learned a lot over the last 7 years. And today, it's correct that I would split my answer two sides. From the hardware perspective, we do evolve over time. Maybe not as much as, maybe not revolutionary, but it's very different. The architecture is very different than the NeuPro-S. So as you see here, we have many more accelerators. We adapt to the use cases and what is needed in the market. And then the side that we actually not evolving as much, but I think it's actually because we don't need to, is the software side. So software side, even if you're a new startup that has hardware solution, it takes many years to get to software that is mature, stable, and able to have a good solution. And we learned that the hard part, right? We're in the DSP market for 30 years. We're in the AI market for 7, 8 years. So software, takes a lot of time to mature. And when we come to updating our software to the NeuPro-M, yes, there's a lot of work because the architecture is different. There are many engines, but we utilize what we already have. We utilize our feedback from customers, the new requests that we have from customers that actually gives us a lot of strengths over someone that is new in the market because we have a big base that, guys coming and saying, hey, but we need this now. Okay, we can support it on an existing platform, but we can do a much better job if we update the hardware in the new platform. And this actually, I think, is to our strengths. The capability of experience and expertise, and a good customer base for that.
Okay. Audience questions. There we go.
A quick question. Just wondering, you've got a lot of different hardware engines in there. How does that look from the programmer point of view? Are those like abstracted away and your compiler takes care of it, or do you write specific code for each accelerator, like the Winograd or the other accelerators?
Right, yeah, so this is some of the features that we added, like the control scheme, will actually enable the toolset, the CDNN, to be able to utilize all the different elements together at the same time. So the idea is that the CDNN tool is utilizing the hardware. The user has control, meaning he can say, I want to turn on or off the different blocks, like I want to turn on and off the Sparsity, I want to turn on or off the Winograd. But the idea is that the CDNN is basically taking the network and optimizing and utilizing all the hardware. So the user does not have to actually go and manually program each of these things. So it's the hardware that is here to serve the software, but the user has the levers. I want to use this more. I want to optimize the different features so that it has visibility of what the tool is doing, and it can configure the tool set. So the more we invest and add more features to the tool set, over time it makes automation makes it easier for the developer to update things. And CDNN, as I mentioned, was the first in the market 2015 that actually did the quantization automatically. And this is the goal also here, to automate the migration from the training of the network to actually running it optimized very efficiently on the hardware.
With that, we're out of time. Another round of applause for Yair.